A shooting star blurs past, a fleeting cosmic messenger. But what if an object moved so fast it could circle our entire planet in less than a second? The universe is filled with speed demons that defy all common sense, from tiny ghostly particles to stars flung from galaxies. By the end of this journey, you will know the 30 most astonishing facts about the fastest things in existence. We will uncover what propels a star to millions of miles per hour and confront the mysterious particles that arrive from deep space, moving at almost impossible velocities. What single force do you think drives the ultimate speed limit of reality itself? This ultimate speed limit is the speed of light, a universal constant represented by the letter c. It is precisely 299,792,458 meters every single second. Think about that number for a moment. It is not just a suggestion or a temporary barrier. It is a fundamental rule woven into the fabric of reality itself. Nothing that has any mass at all can ever reach this speed, let alone exceed it. The closer an object with mass gets to c, the more energy is required to push it even a little bit faster, with the energy demand becoming literally infinite at the speed of light. This is why the universe has a maximum velocity, but this rule is about far more than just light or travel. It is the speed of causality. It is the maximum speed at which any information, any influence, any cause can create an effect across the cosmos. This single number, c, is why you cannot change the past. The light from events long ago is only just reaching us now, and we can do nothing to affect what has already happened from our distant vantage point. This cosmic speed limit defines the very structure of space-time, creating the unbreakable order of cause and effect that makes our universe logical and predictable. That cosmic speed limit is absolute, yet it does not stop the universe from creating objects that push right up against its edge. Far beyond our solar system, entire stars are being catapulted into the endless dark. These are hypervelocity stars, and they are some of the fastest single objects we have ever witnessed. Their incredible journeys begin in the most chaotic place imaginable, the very center of a galaxy. Lurking there is a supermassive black hole, a gravitational monster with the mass of millions or even billions of suns. When a double star system, two stars orbiting one another, wanders too close to this cosmic beast, a violent gravitational dance unfolds. The black hole's immense pull can capture one star while violently flinging the other away at a staggering fraction of light speed. It is a gravitational slingshot of unimaginable power. One famous example is a star known as S5HVS1, discovered racing through our own Milky Way. This stellar cannonball is moving at over 1,700 kilometers per second. At that speed, it is not just strolling through the galaxy, it is making a permanent escape, flying out into the intergalactic void where it will spend eternity completely alone. This slingshot mechanism transforms the black hole's destructive potential into a stellar launching system, proving that even the most terrifying forces in the cosmos can create breathtaking phenomena. But that black hole slingshot is not the only way nature achieves staggering velocities. Some of the fastest spinning objects in the universe are born from stellar death itself. When a massive star explodes in a supernova, its core can collapse into an unimaginably dense ball called a neutron star. Just a single teaspoon of this material would weigh billions of tons. And some of these neutron stars become pulsars, cosmic lighthouses that sweep the darkness with beams of radiation. The fastest of them all are the millisecond pulsars, spinning so rapidly they complete hundreds of full rotations every single second. Now try to picture the surface of one of these stars. While the entire object might only be the size of a city, its equator is whipping around at a substantial fraction of the speed of light. We are talking about velocities that could be a quarter or even half of light speed. This means a point on its surface is moving at tens of thousands of kilometers per second. This ferocious spin generates magnetic fields trillions of times stronger than Earth's and focuses intense beams of energy from its poles. Each time one of these beams sweeps across our line of sight, we detect a pulse like a lighthouse beacon from across the galaxy. The stability of these pulses is so perfect that they rival atomic clocks. So, within the eerie calm after a star's violent death, we find a spinning remnant that defies all intuition, a testament to the fact that in the cosmos, even destruction can give rise to objects of breathtaking precision and speed. Yet even the blistering spin of a pulsar is dwarfed by a far grander spectacle. Deep within the hearts of the most active galaxies, a truly colossal engine is at work. Here, a supermassive black hole, feasting on a swirling disk of gas and dust, does more than just consume. It unleashes twin beams of pure energy and matter, firing them from its poles into the depths of intergalactic space. These are relativistic jets, and they are the largest and fastest directed flows of material in the entire known universe. The matter within these jets is not just hot gas, it is a plasma, a seething soup of charged particles accelerated by unimaginable magnetic fields. These particles are forced along magnetic field lines that act like the barrel of a cosmic rifle, channeling them into narrow, focused beams that can travel for hundreds of thousands of light years. Their speed is almost incomprehensible. We are not talking about a fraction of light speed. We are witnessing matter that travels at over 99% of the universe's ultimate speed limit. At such extreme velocities, the laws of relativity warp our very perception. Time dilates and lengths contract from our point of view. The energy released is so immense that these jets shine with a ferocious glow across the entire electromagnetic spectrum, from radio waves to the most powerful gamma rays. When one of these beams, by sheer chance, is pointed almost directly at Earth, we see a blazar, an object that can outshine every star in its host galaxy combined. These are not just distant curiosities, they are fundamental proof that black holes are not merely destructive voids, but can also act as the most powerful particle accelerators in existence, shaping the cosmos on a truly monumental scale. While these colossal jets illuminate the heavens, a far more subtle and relentless rain of particles is constantly striking our planet. Cosmic rays are not rays of light at all, but rather a hail of subatomic bullets, mostly single protons, arriving from every corner of the cosmos. They are the fastest individual pieces of matter we have ever detected, and their energies defy belief. The most powerful of these particles ever recorded was so astonishing it earned the nickname the "Oh my God" particle. This single proton, a fragment smaller than an atom, was moving with so much kinetic energy it was like a Major League Baseball speeding toward home plate. Its velocity was an almost incomprehensible 99.999999999999999% of the speed of light. Think about how close that is to the universe's absolute limit. That single proton was only barely, infinitesimally slower than light itself, carrying the energy of a brick dropped from waist height, all packed into a particle a trillion times smaller than a grain of sand. This creates one of the greatest ongoing mysteries in astrophysics. What cosmic engine in the universe could possibly launch a single, tiny proton with such ferocious power? The origins of these ultra-high-energy cosmic rays remain largely unknown, though scientists suspect they are born in the most violent events imaginable, perhaps from the shockwaves of supernova remnants, the chaotic environments around supermassive black holes, or from colliding galaxies. Every second, thousands of these cosmic messengers pass straight through your body, silent and harmless, each one a tiny, unsolved piece of a much larger puzzle. Yet that cosmic speed limit for objects within space reveals an even deeper truth about the universe's own architecture. The very fabric of the cosmos is stretching, and this expansion can achieve velocities that seem to break all the rules. We observe galaxies so incredibly distant that they appear to be flying away from us at speeds greater than light. This is not a violation of Einstein's relativity, however, because these galaxies are not hurtling through space on their own power. Instead, the space between us and them is itself expanding, carrying the galaxies along like raisins in a rising loaf of bread. The farther away a raisin is, the more dough there is between it and you, so the faster it appears to recede. For galaxies at the very edge of our observable universe, the cumulative stretching of all that space results in a recession velocity that truly does exceed the speed of light. This phenomenon is one of the cornerstone pieces of evidence for the Big Bang, painting a picture of a universe that has been growing from an incredibly dense, hot state for nearly 14 billion years. More than that, the discovery that this expansion is actually accelerating points to the mysterious influence of dark energy, a force that seems to be woven into the vacuum of space itself, relentlessly pushing the cosmos apart. So the ultimate speed record does not belong to any single object, but to the universe's own stretching canvas, a fundamental process that dictates the ultimate fate of everything we see. Even the architects of cosmic chaos can themselves be thrown into the void. We have seen stars flung from galaxies, but what about the black holes that did the flinging? It turns out these gravitational monsters can also become cosmic fugitives, ejected from their home galaxies to wander the eternal dark. This incredible phenomenon is known as a runaway black hole, and it begins with a collision of titans. When two galaxies merge, the supermassive black holes at their cores eventually sink to the center and begin a deadly orbital dance. As they spiral inward, they radiate energy in the form of gravitational waves, ripples in the fabric of spacetime itself. If these two black holes are of unequal mass or have misaligned spins, the final merger can act like a cosmic rocket engine. The newborn, more massive black hole can receive a powerful kick, a recoil from the lopsided blast of gravitational waves. It is shot out from the galactic center at speeds that can reach thousands of kilometers per second, millions of miles per hour. This is not a slow drift, it is a violent expulsion. Imagine a behemoth with the mass of millions of suns, a force that once governed an entire galaxy, suddenly cast out into the emptiness between galaxies. It travels alone, a dark predator in an ocean of nothing, often dragging its accretion disk of glowing gas along with it like a ghostly comet's tail. This reveals a universe of profound dynamism, where even the most dominant forces are not permanent fixtures, but temporary players in an endless gravitational ballet. But our own species is not content to merely observe these cosmic speed records from afar. We are building our own contenders. The fastest human-made object ever created is not a deep space probe headed for the stars, but a spacecraft flying directly into the inferno of our own sun. The Parker Solar Probe is a technological marvel, a shield-clad explorer on a mission to touch the very face of our star. To achieve the immense speed required for its daring orbits, the probe performs a breathtakingly precise gravitational dance with the planet Venus. Each time it swings past Venus, the planet's gravity acts like a cosmic brake, stealing a tiny bit of the probe's orbital energy and allowing the sun's immense gravity to pull it even closer on its next pass. This series of calculated maneuvers is what allows it to reach its staggering top speed of over 690,000 kilometers per hour. At that velocity, you could travel from New York to Tokyo in less than a minute. Its primary mission is to solve two of the sun's most enduring mysteries, the origins of the solar wind and the puzzle of coronal heating. The solar wind is a constant stream of charged particles flowing from the sun, shaping the space environment throughout our solar system and causing phenomena like the auroras. But what accelerates this wind to such high speeds? Even more perplexing is the sun's corona, its outer atmosphere. Logic would suggest that the surface of the Sun is hotter than the atmosphere above it, but the corona is mysteriously superheated to millions of degrees. The Parker Solar Probe flies through this million-degree plasma, its revolutionary heat shield glowing red-hot as it endures temperatures that would vaporize almost any other spacecraft. By directly sampling the Sun's atmosphere, it is sending back data that is fundamentally rewriting our textbooks, helping us understand the very forces that drive space weather, which can impact satellites and power grids on Earth. This tiny human-built object racing through a stellar furnace is a testament to our enduring curiosity and our desire to not just watch the universe's fastest phenomena, but to fly directly into them. The violent recoil that flings a black hole across space does not vanish without a trace. It sends out a message. These messages are gravitational waves, ripples in the very fabric of space-time that race outward at the speed of light. Albert Einstein predicted their existence over a century ago, but he thought they would be far too weak for us to ever detect. He was wrong. In 2015, a revolutionary experiment called LIGO heard the unmistakable chirp of two black holes, each about 30 times the mass of our Sun, spiraling into each other over 1 billion light-years away. In the final fraction of a second before they merged, these colossal objects whipped around each other at nearly half the speed of light, churning the space-time around them like a spoon stirring a pot of honey. The energy they released in that instant, purely in the form of these invisible ripples, was greater than the combined light output of every single star in the observable universe. Think about that scale for a moment. Every galaxy, every quasar, every shining sun, outshone in pure energy by a silent, invisible shudder in the cosmos. Since that first detection, we have listened to the collisions of neutron stars, events that also shine in light, gamma rays, and even gold. These cosmic crashes forge the heavy elements that make up our world and our very bodies, proving that the fastest phenomena are not just destructive, but are essential creators, weaving the fabric of reality itself with every cataclysmic tremor. That same gravity which sends ripples through space-time also creates some of the most luminous and violent whirlpools in the cosmos. Around a black hole or a neutron star, a doomed river of superheated gas and plasma forms a structure called an accretion disk. This is not a gentle, swirling cloud. It is a maelstrom of matter spiraling inward at velocities that can reach half the speed of light or more, a chaotic frenzy driven by unimaginable gravitational pull. Picture a bathtub drain, but one where the water is a million-degree inferno and the drain leads to a point of infinite density. As this material is pulled inward, it does not fall straight in. Conservation of angular momentum forces it to spiral like water circling a drain, and in this cosmic whirlpool, the particles rub against each other with ferocious intensity. This friction, combined with the shear from the different orbital speeds of the inner and outer disk, generates so much heat that the disk does not just get warm. It glows with a blinding incandescence, shining across the entire electromagnetic spectrum from radio waves to X-rays. This is the primary reason we can even detect many black holes, as they are invisible themselves but revealed by the brilliant, screaming light of the matter they are consuming. Within this chaotic disk, magnetic fields become tangled and amplified, acting like cosmic slingshots that can fling material away or channel it into the powerful relativistic jets we see erupting from the poles. This dazzling light show, visible across billions of light-years, is the final, radiant scream of matter being accelerated to relativistic speeds before it crosses the point of no return, vanishing forever from our observable universe. While matter screams its final song in an accretion disk, the cosmos also speaks in a language of pure, fleeting energy. Fast radio bursts are among the most puzzling signals we have ever detected, intense blasts of radio waves that flash into existence for barely 1,000th of a second and then vanish forever. In that single millisecond, an average fast radio burst can release more energy than our Sun will emit over 80 years. The sheer power is staggering, a cosmic shout that crosses billions of light-years of space to reach our telescopes. The signals themselves, being radio waves, travel at the speed of light, the only speed at which information can cross such vast distances. But what could possibly create such a brilliant, brief flash? The leading suspect is a type of stellar corpse called a magnetar. Imagine a neutron star, already a city-sized object of incredible density, but then crank its magnetic field up to an almost unimaginable intensity. A magnetar's magnetic field is 1,000 trillion times stronger than Earth's. If one were located halfway between Earth and the Moon, it would erase the magnetic strips on every credit card on our planet. The leading theory suggests that these magnetic fields are so powerful they can literally crack the star's solid crust, causing a starquake that unleashes a catastrophic rearrangement of the magnetic field. This sudden release of magnetic energy is like a cosmic circuit shorting out, firing a focused beam of radio waves across the universe. We see it as a single, blinding spike on our instruments, a 1-millisecond testament to a violent event that occurred in a distant galaxy long before Earth even formed. These bursts are so fast and so random that catching them is like trying to spot a single camera flash on a planet 1,000 light-years away, a reminder that the universe is filled with transient whispers and shouts we are only just beginning to hear. That very expansion creates a fundamental limit to our vision, a final horizon for the entire cosmos. We call it the cosmological horizon, and it represents the ultimate edge of everything we can ever possibly know. As dark energy relentlessly pushes the fabric of space apart, galaxies beyond a certain critical distance are carried away from us so quickly that their light, racing toward us at the speed of light itself, is fighting a losing battle against the stretching void. The space between us and that light is expanding faster than the light can traverse it. Imagine a swimmer trying to cross a river that is widening more quickly than they can swim. No matter how strong they are, they will never reach the other side. In the same way, the light from those incredibly distant galaxies is destined to travel forever through an ever-growing gulf, its journey never complete. This means there are entire galaxies, entire civilizations of stars, whose photons will simply never, ever reach our telescopes. They are not just far away, they are permanently and forever hidden from our view, receding into a superluminal zone we can never access. The light they are emitting right now is falling behind in the cosmic race, destined to grow ever fainter and redder until it effectively vanishes from our detectable reality. Every second that passes as the expansion accelerates, this horizon subtly shrinks our observable universe, locking away more and more of creation into an unreachable past. We are left on our island of visibility, watching the shorelines of the knowable cosmos slowly recede into an eternal, impenetrable dark. Even the most colossal explosions in the universe produce messengers that are almost nothing at all. Neutrinos are the universe's ghost particles, so ethereal they can pass through a light year of lead without a single collision. Born in the nuclear fires of stars like our Sun, and in the cataclysmic blasts of supernova, these particles carry almost no mass and no electric charge. This lack of interaction is precisely what allows them to flee a dying star's core at the moment of collapse, often outpacing the light of the explosion itself. They almost always travel at speeds so phenomenally close to the speed of light that, for all practical purposes, they are racing alongside photons. Right now, as you watch this, trillions of solar neutrinos are passing straight through your body and through the entire Earth beneath you every single second, completely unnoticed. Their ghostly nature makes them incredibly difficult to catch, forcing scientists to build enormous, ingenious detectors deep underground. These facilities, like the Super Kamiok and in Japan, use immense tanks of ultra-pure water, waiting in darkness for the vanishingly rare moment a neutrino finally bumps into an atomic nucleus. When it happens, it produces a faint, telltale flash of blue light called Cherenkov radiation, a fleeting signature of a ghost's touch. These elusive particles are cosmic couriers, delivering untampered information from the hearts of stars and the most violent stellar deaths, a silent, high-speed whisper from the universe's most energetic engines. That faint whisper of a fast radio burst is nothing compared to the universe's most violent scream. Gamma-ray bursts are the single most energetic explosions known to exist since the Big Bang itself. In a span of seconds, a single burst can release more energy than our Sun will emit across its entire 10 billion-year lifespan. This is not a gradual release, but a sudden, catastrophic detonation of pure power. We now understand these events are the birth cries of new black holes or the final, shattering collisions of neutron stars. When two impossibly dense neutron stars spiral into each other, they rip themselves apart in a kilonova explosion, forging heavy elements like gold and platinum while collapsing into a newborn black hole. In both scenarios, the cataclysm unleashes twin jets of plasma from its poles, beams of focused fury that punch their way out of the stellar wreckage. The particles within these jets are accelerated to velocities that defy comprehension, reaching 99.9999% of the speed of light. This is the realm of ultra-relativistic motion, where matter is pushed so close to the cosmic speed limit that its behavior becomes governed entirely by the strange laws of Einstein's relativity. The energy of the explosion is so tightly focused into these narrow beams that we only detect a gamma-ray burst if one of those deadly lances is pointed directly at Earth. From our fortunate, distant vantage point, we witness a fleeting flash of the highest energy light, a brief signal that marks the death of a star and the violent creation of something new in the profound darkness. Even our galaxy's central monster is not the final authority. At the very heart of the Milky Way, a supermassive black hole named Sagittarius A holds sway, a gravitational titan with the mass of 4 million suns. Yet for all its power, it is not sitting still. Astronomers have discovered that this colossal object is itself in motion, orbiting an unseen point at a brisk pace of around 200 kilometers per second. It is a slow, stately dance, but a dance nonetheless. The question is, what could possibly serve as a gravitational anchor for something so immense? The black hole is not simply wandering. Its motion suggests it is responding to a truly staggering concentration of mass located somewhere nearby in the galactic core. This invisible partner cannot be a cluster of normal stars, as the combined light of such a vast number would be easily visible to our telescopes. The leading theory points to an immense, dense knot of dark matter, the mysterious substance that makes up most of the galaxy's mass but refuses to interact with light. This unseen halo could be acting as the central weight around which everything, including the black hole, revolves. Another possibility is the lingering gravitational scar from a past galactic merger, the ghost of a smaller galaxy and its own black hole that was consumed by the Milky Way eons ago. This motion reveals that even the most dominant forces are part of a larger gravitational system, a cosmic hierarchy where nothing, not even a supermassive black hole, is truly at the center of it all. That stately motion of our galaxy's central black hole is just a single step in a much grander cosmic dance. Our entire Milky Way, along with its countless stars and neighboring galaxies, is part of a vast celestial structure known as the Laniakea supercluster. This is our home on the most immense scale, a sprawling web of over 100,000 galaxies, all bound together by the invisible threads of gravity. Yet this entire continent of galaxies is not sitting still. It is adrift in the cosmic ocean, pulled by forces we are only beginning to understand. Our galactic supercluster is flowing as a single entity at a breathtaking speed of over 600 kilometers per second. We are all moving toward a mysterious, unseen concentration of mass that astronomers call the Great Attractor. This name alone evokes a sense of cosmic wonder and profound mystery. It lies in the direction of the constellation Centaurus, hidden from our direct view by the dense clouds of stars and dust in our own Milky Way's galactic plane. For decades, this region was a literal blind spot in our maps of the universe. What we do know is that the gravitational pull emanating from this point is so immense that it is drawing in countless galaxies, including our own, in a slow but relentless current. This motion reveals that the universe is not just expanding uniformly in all directions, but is also filled with these subtle rivers and flows, a cosmic choreography dictated by the uneven distribution of matter, both seen and unseen. The Great Attractor itself appears to be just one waypoint in an even larger flow, as we, along with the Great Attractor, are being pulled toward an even more massive structure known as the Shapley supercluster, the single largest concentration of mass in our observable universe. So every single star, every planet, every one of us is caught in this vast, multi-layered current, racing toward a hidden gravitational heart at a speed of over 2 million miles per hour. But the universe's speed limit is not just a barrier, it is also a source of profound speculation. What if something could simply be born on the other side of that line, traveling forever faster than light? Theoretical physics offers a name for such an entity, the tachyon. This is not a particle we have ever detected or even truly expect to find, but a hypothetical concept that emerges from the mathematics of Einstein's equations. According to the theory, a tachyon would possess an imaginary mass, a mathematical construct that is difficult to visualize but would have one clear consequence: it could never slow down to the speed of light or below. Its entire existence would be lived in a superluminal realm, a state of being forever beyond our direct perception. This leads directly to a universe of paradox. The most jarring is the violation of causality, the very foundation of cause and effect. If a tachyon could be used to send a signal, it could theoretically arrive at its destination before it was ever sent. You could receive a message warning you not to send it, creating a logical loop that shatters our understanding of time itself. For this reason, most physicists consider tachyons a mathematical curiosity rather than a physical reality, a ghost in the equations that points to the absolute nature of light speed. Yet this very strangeness has cemented their place in science fiction and in our deepest thought experiments, forcing us to question the rigid structure of reality and wonder what truly lies beyond the ultimate cosmic boundary. The illusion of faster-than-light travel is not just a theoretical concept, it is something we have directly witnessed. One of the most stunning examples comes from the first quasar ever identified, a brilliant beacon known as 3C273. Quasars are the intensely luminous cores of distant galaxies, powered by supermassive black holes feeding on enormous amounts of gas. 3C273 is so bright it can be seen from over 2 billion light-years away. But its true marvel lies in a jet of matter erupting from its core, a stream of plasma that the Hubble Space Telescope has studied in exquisite detail. Hubble observed bright knots within this jet, blobs of superheated material that appeared to be moving at a staggering 6 times the speed of light. This superluminal motion is a breathtaking cosmic illusion, a trick of perspective born from relativistic velocities. The material in the jet is not actually breaking the universe's speed limit. Instead, it is racing toward us at over 99.9% of the speed of light, traveling almost directly along our line of sight. As a new blob forms and begins its journey, it emits light. This light, traveling at light speed, has a shorter distance to reach us than the light emitted by the blob an instant later, because the blob itself is almost keeping pace with its own radiation. Our perception compresses the time between these light arrivals, making it seem as though the blob has crossed a vast distance in an impossibly short time. It is like watching a plane on a landing approach, where it seems to float slowly even though it is moving hundreds of miles per hour. In the case of this quasar's jet, the effect is magnified to an extreme that challenges our very perception of reality, showing us that at the universe's ultimate velocities, even what we see cannot be taken at face value. Even the grand spirals of galaxies hold a secret about motion. A galaxy like our own Milky Way is not a solid, spinning pinwheel. Instead, it is a vast collection of billions of individual stars, each tracing its own orbital path around the galactic center. The beautiful spiral arms we see are not permanent structures made of the same stars, but rather like a cosmic traffic jam, a pattern of compressed density that moves through the galactic disk. This pattern is called a density wave. Picture an endless stream of cars on a circular freeway. If one group of cars slows down slightly, it creates a visible, slow-moving knot of congestion, even though individual cars are constantly entering and leaving that knot, speeding up again once they get through. In a galaxy, this density wave is the spiral arm. As clouds of gas and dust enter this compressed region, the increase in density triggers the collapse of these clouds, igniting the brilliant blue stars that outline the arm. The wave itself propagates at its own stately pace, while the stars and gas clouds orbit at different, often faster speeds, continuously moving in and out of the pattern. This elegant mechanism solves the winding problem, explaining why spiral arms do not simply get wound up tightly and vanish over billions of years. Yet this graceful dance also revealed one of the universe's greatest mysteries. By studying the orbital speeds of stars at different distances from a galaxy's center, astronomers made a shocking discovery. According to the laws of gravity, stars on the outer fringes of a spiral galaxy, far from the central bulge of visible mass, should be orbiting much more slowly. But they are not. These distant stars race around at nearly the same high speed as those closer in. The only plausible explanation is that the entire galaxy is embedded within an immense, invisible sphere of matter, a halo of dark matter whose gravitational pull is the true conductor of this cosmic orchestra. The beautiful, swirling pattern of a spiral galaxy is therefore a luminous tracer, a fleeting pattern of light moving through a hidden sea of something we cannot see, but whose gravitational influence dictates the very speed of the stars themselves. Our own star is a constant reminder that cosmic speed is not just a distant spectacle. The sun regularly unleashes its own fury in the form of solar flares and coronal mass ejections. These are not gentle puffs of solar wind, but titanic explosions that rip billion-ton clouds of superheated plasma directly from the sun's atmosphere and hurl them into the void. The speeds involved are staggering, ranging from a relatively sedate 250 kilometers per second to an outright terrifying 3,000 kilometers per second. At their fastest, these projectiles can cross the 150 million kilometer gulf from the Sun to Earth in less than a day. When such a cloud, known as a coronal mass ejection, is aimed directly at our planet, it carries with it the potential for chaos. The real danger lies not in the cloud itself, but in the intense magnetic fields and swarms of high-energy particles it carries. As this solar tsunami washes over Earth, it compresses our planet's protective magnetic field, inducing powerful electrical currents in the ground. These geomagnetically induced currents can overload power grids, causing widespread blackouts that could last for weeks or even months. In 1989, a powerful solar storm caused the entire power grid in Quebec, Canada, to fail in seconds, leaving millions in the dark. For astronauts aboard the International Space Station, such an event is a direct threat, forcing them to take shelter in more heavily shielded segments of the station to avoid a dangerous radiation dose. Even our ubiquitous satellites are at risk, their delicate electronics vulnerable to being fried by the onslaught of charged particles. This is why space weather forecasting has become so critical. Scientists constantly monitor the sun, watching for the telltale signs of an impending eruption, giving us precious hours to prepare, to safeguard our fragile technological civilization from the raw, high-speed power of our own star. While our fastest probes are still racing toward the stars, we have already cast a few tiny messengers into the cosmic ocean beyond our sun's influence. The Pioneer and Voyager probes are now interstellar travelers, carrying with them the faint echoes of humanity's curiosity. Their incredible journeys were powered not by colossal engines, but by a clever cosmic trick, gravity assist. This technique uses the gravity of a planet as a slingshot, stealing a tiny bit of the planet's own orbital momentum to dramatically boost a spacecraft's speed. Voyager 2 famously used a grand tour, swinging past Jupiter, Saturn, Uranus, and Neptune, each encounter whipping it faster and altering its course. The result of these celestial billiard shots is a velocity that defies our initial power. Voyager 1, the most distant human-made object, is now racing away from the Sun at about 17 kilometers per second. That is over 38,000 miles per hour, a speed that allowed it to achieve a monumental first. In August of 2012, Voyager 1 crossed the heliopause, the invisible boundary where the Sun's inflating bubble of solar wind finally yields to the pristine plasma of interstellar space. It had officially left our solar system, becoming a permanent citizen of the galaxy. These silent, golden records carrying greetings from Earth are now drifting through the void between the stars, a testament to a species that dared to reach beyond its own celestial backyard, sending its first artifacts into the great dark. These stellar deaths make a typical supernova look like a gentle flicker. When the most massive stars in the universe, those spinning at a ferocious pace, reach the end of their lives, they do not just explode. They undergo a catastrophic collapse so complete and violent that it forges a hypernova. Unlike a standard supernova, which leaves behind a dense neutron star, a hypernova occurs when the star's core is so immense and its spin so rapid that it bypasses the neutron star stage entirely. It collapses straight past that point of no return, instantly birthing a black hole. This is not a simple core collapse, it is a total gravitational surrender. The entire stellar core, with a mass dozens of times that of our Sun, plummets directly into oblivion. In that final, dizzying instant, the star's incredible rotational energy is not lost. It is focused as the inner material funnels into the newborn black hole. The conservation of angular momentum acts like a figure skater pulling in her arms, causing the surrounding accretion disk to spin at a blinding rate. This creates a powerful dynamo, channeling the star's remaining energy into two narrow, opposing beams that scream outward from its poles. These are the relativistic jets, and they are the true power behind the most long-lasting and energetic gamma-ray bursts we see across the cosmos. For dozens of seconds, these jets, composed of matter accelerated to within a hair's breadth of light speed, drill their way out through the dying star's outer layers. When they finally break free, they unleash a focused torrent of gamma radiation into the universe, a final, brilliant testament to a star that did not just die, but transformed itself into the most powerful particle cannon imaginable. Our entire solar system is a ship on a vast, silent voyage. While we feel stationary on the Earth's surface, the Sun is pulling us and all the planets on a grand orbit around the center of the Milky Way. We are moving at a breathtaking 220 kilometers every single second. That is nearly 500,000 miles per hour. At this incredible speed, you would think we would complete a lap of the galaxy quickly. But the scale is so immense that a single orbit, one galactic year, takes approximately 230 million of our Earth years. The last time our solar system was in this particular position in its galactic orbit, the dinosaurs were just beginning their long reign on Earth. That is the profound scale of a single cosmic year. Yet this motion is not perfectly smooth. Our Sun also has a slight wobble, a peculiar motion relative to the local standard of rest, which is the average movement of all the nearby stars in our galactic neighborhood. This means our solar system is gently bobbing up and down as it orbits, moving through the galactic plane like a car on a slightly bumpy road. So every moment of your life, you are a passenger on this magnificent journey, racing around a galactic center you will never see with your own eyes, completing a circuit so vast it defines epochs of life on our planet. Deep within the dusty heart of our own galaxy, a smaller but no less violent drama unfolds. A peculiar object known as the Great Annihilator, officially catalogued as 1E1740.7-2942, lurks near the galactic center. It is a microquasar, a stellar mass black hole that mimics on a smaller scale the behavior of its supermassive cousins in distant galaxies. This particular black hole, perhaps 10 times the mass of our Sun, is feeding on a companion star, pulling gas from it into a searingly hot accretion disk. But the Great Annihilator earns its ominous name from what happens next. From its poles, it fires twin jets not just of ordinary matter, but of electrons and their antimatter counterparts, positrons. A positron is the electron's perfect mirror, identical in mass but possessing a positive electrical charge. When a jet of these positrons, traveling at a substantial fraction of light speed, collides with the normal matter floating in interstellar space, the result is mutual annihilation. Electron meets positron, and both particles vanish in a flash of pure energy, releasing 2 gamma-ray photons. This constant, high-energy fireworks display is what makes the Great Annihilator shine so brightly in the gamma-ray part of the spectrum, a beacon of destruction and creation happening right in our cosmic backyard. This microquasar serves as a perfect nearby laboratory, showing us how the same fundamental physics that power distant quasars also operates on a smaller, more intimate scale, proving that the universe's most energetic processes are not confined to the far reaches of space, but are actively at work all around us. This grand galactic flow reveals a subtle but critical distinction in how everything moves. Every galaxy we observe is subject to 2 very different kinds of motion. The first is the Hubble flow, the relentless river of cosmic expansion that carries galaxies apart as the very space between them stretches. This is the primary motion for most distant galaxies, a smooth and stately recession. But superimposed on this universal drift is a second, more local motion, what astronomers call a peculiar velocity. This is a galaxy's own individual speed, caused by the gravitational tugs from its immediate neighbors and the massive structures of the cosmic web. It is the difference between floating down a wide, slow river and actively swimming across the current. The most stunning example of this is happening right in our own cosmic backyard. The Andromeda Galaxy, our closest large galactic neighbor, is not receding from us with the Hubble flow. In a profound violation of the expanding universe trend, it displays a blue shift. Its light is compressed, telling us it is hurtling directly toward the Milky Way at an incredible 110 kilometers per second. This is not because expansion has reversed for us, but because our mutual gravitational attraction is so strong it has overcome the Hubble flow on this local scale. Our 2 galaxies are swimming vigorously against the cosmic current, drawn together by gravity's inexorable pull, destined to merge in a colossal dance billions of years from now. This duality of motion defines the cosmos, a universe where everything is both carried by the tide and navigating its own unique path through the void. The most powerful magnetic fields in the universe belong to a specific type of stellar corpse known as a magnetar. These are neutron stars, but they are born spinning so ferociously that their internal magnetic fields become wound up and amplified to an almost unimaginable intensity. A magnetar's magnetic field is so strong it fundamentally warps the very atoms on its surface, creating a crust of iron that is harder than diamond and under immense strain. This crust is not perfectly smooth. It builds up stress over time until it finally fractures. This event is a starquake, a seismic shift on a cosmic scale. When the crust of a magnetar cracks, it releases more energy in a fraction of a second than our Sun will emit in 100,000 years. The entire star rings like a bell, vibrating violently. But the real power comes from the magnetic field itself, which is suddenly and catastrophically rearranged. This magnetic upheaval acts like a colossal particle accelerator, whipping the charged particles in the star's atmosphere to velocities incredibly close to the speed of light. The result is a blinding flash of high-energy radiation, a burst of X-rays and gamma rays so intense it can temporarily outshine every other source in the gamma-ray sky, including our entire galaxy. For a brief moment, this single, city-sized object becomes the brightest thing in the universe outside of a gamma-ray burst. These starquakes are fleeting, lasting only milliseconds, but they leave a permanent record across space, another stark reminder that the cosmos is filled with sudden, violent releases of energy that operate on a scale far beyond our everyday experience. Far beyond the orbit of Neptune, in the profound and permanent dark, lies a frozen reservoir of ancient ice. This is the Oort cloud, a vast spherical shell of trillions of icy bodies enveloping our solar system like a distant, ghostly shroud. These objects are not in stable orbits. They are barely bound to the sun at all, drifting in a gravitational twilight zone. All it takes is the gentlest of cosmic nudges to set one of these sleeping giants on a new path. That nudge can come from the gravity of a star passing millions of years ago in our galactic neighborhood, its subtle pull felt across the light years. It can even come from the Milky Way itself, as the galactic tide, the cumulative gravity of all the stars and dark matter in the galactic disk, tugs at these distant objects. This delicate gravitational perturbation is enough to dislodge a comet, upsetting its fragile balance and sending it tumbling inward. At first, its motion is slow, a lazy fall from the outer dark. But as the sun's gravity takes hold, the fall becomes a plunge. The comet accelerates, its speed increasing dramatically as it surrenders to the star's pull, transforming its potential energy into raw, kinetic velocity. What began as a barely moving chunk of ice at the solar system's edge becomes a dazzling streak across our inner sky. A visitor from the deepest cold now racing through the warmth of the inner planets, its long tail a brilliant testament to the fragile connections that tie our entire solar system to the galaxy beyond. This special alignment gives us a front-row seat to the most extreme physics in the universe. Blazars are a specific type of active galaxy, and their defining feature is a matter of pure chance and perspective. They are essentially quasars whose powerful relativistic jets are aimed almost directly at our line of sight. We are staring straight down the barrel of a cosmic cannon. This precise alignment triggers effects predicted by Einstein's special relativity that dramatically amplify what we see. Because the material in the jet is racing toward us at over 99.9% of the speed of light, the light it emits gets bunched up, much like the sound waves from an approaching ambulance are compressed into a higher pitch. This relativistic beaming effect concentrates the radiation, making the blazar appear hundreds or even thousands of times brighter than it would if the jet were pointed in any other direction. The light is also blue-shifted, boosted to higher energies, but the strangest consequence is time dilation. From our distant perspective, clocks within the jet would appear to be ticking in slow motion. Events that might take hours from the jet's own frame of reference are compressed into minutes or even seconds from our point of view. This is why blazars are notorious for their extreme variability. They can flare up, doubling in brightness in a matter of hours, and then just as quickly fade away. We are witnessing the inner workings of a relativistic engine in what seems like fast forward, a flickering beacon that allows us to probe the conditions within these jets, testing the laws of physics in an environment of pure, accelerated fury. That search for intelligent signals brings us to one of the most tantalizing mysteries in the history of astronomy. On August 15, 1977, a radio telescope at Ohio State University known as the Big Ear recorded something extraordinary. A volunteer astronomer named Jerry Amon was reviewing the printout days later when his eyes fell upon a string of data so shocking he circled it and wrote a single, breathless word in the margin: "Wow." The signal was a powerful, narrowband radio burst, precisely the kind of signature predicted for an artificial transmission from an advanced civilization. It lasted for 72 seconds, rising and then falling in intensity just as you would expect from a signal sweeping across a fixed telescope due to Earth rotation. It came from a region of space in the constellation Sagittarius, and then it was gone. Despite numerous attempts over the decades to find it again, the signal never repeated. If the WOW signal was indeed a message, it traveled across the cosmos at the ultimate speed for information, the speed of light. This means the event itself, whatever caused it, happened long before humans ever built radio telescopes, and our chance to hear it was a fleeting coincidence in the vast expanse of cosmic time. This single, unverified event galvanized the scientific search for extraterrestrial intelligence, known as SETI. Modern projects use vast arrays of telescopes to scan millions of radio channels simultaneously, hunting for that one in a trillion signal that cannot be explained by any known natural phenomenon. They search for patterns, for repetitive bursts, for anything that carries the unmistakable fingerprint of intelligence. Every second, potential messages from distant stars are crossing the void at light speed, and we are finally, patiently, listening for the next one to arrive. These theoretical engines bring us to the final frontier of speed itself, the ultimate potential for a human-built spacecraft. While our current rockets are bound by the limitations of chemical fuel, physicists and engineers are already sketching out concepts that could push a vessel to a significant fraction of light speed. One of the most dramatic ideas is nuclear pulse propulsion, a system that would literally detonate small atomic bombs behind a spacecraft, letting the shockwaves from these controlled explosions push against a massive pusher plate. It sounds like science fiction, but this was a serious design study known as Project Orion. Such a ship could theoretically reach speeds of up to 10% of light speed, carrying a city-sized payload to the nearest stars within a human lifetime. Another elegant concept is the solar sail, but not one pushed by the gentle pressure of sunlight alone. Imagine a wafer-thin, kilometers-wide sail made of an ultra-light material like graphene. Now picture it being struck not by sunlight, but by a focused array of gigawatt-powered lasers stationed in orbit around Earth. This laser photon sail would be pushed by pure light, accelerating it relentlessly for years until it could reach velocities of 20% or more of light speed. These are not mere daydreams, they are blueprints based on known physics, awaiting only the technological maturity and collective will to build them. But what if we want to go further, to travel to other galaxies within a single human lifetime without violating the cosmic speed limit? This is where the most speculative and mind-bending concept enters the stage, the Alcubierre warp drive. Proposed by physicist Miguel Alcubierre in 1994, this is not an engine that pushes a ship through space. Instead, it would theoretically create a warp bubble around the vessel. Ahead of the ship, spacetime would be massively contracted, while behind it, spacetime would be dramatically expanded. The ship itself would sit in a flat, undisturbed region of spacetime within this bubble, not moving locally at all. In this scenario, the spacecraft would be carried along as the bubble itself moves, effectively riding a wave of distorted spacetime. The fabric of the cosmos itself would be moving faster than light, while the ship remains stationary within its pocket, thus avoiding the infinite energy problem and the violation of causality. The catch is that generating such a warp bubble would require forms of matter and energy with negative mass or negative energy density, things we have not yet discovered or proven to exist. Yet the very fact that such an idea emerges from the equations of general relativity offers a profound sliver of hope. It suggests that the ultimate speed record may not be for any object within the universe, but for our own ingenuity in learning to navigate the universe's deepest laws. The fastest objects we have witnessed are cosmic wonders, but the fastest we might one day build could be the very key to walking among them. From the ghostly whisper of a neutrino to the stately, immense flow of entire superclusters, we have raced alongside the universe's fastest phenomena. We have witnessed stars flung from galaxies, felt the shudder of colliding black holes, and stared down the barrel of a blazar's relativistic jet. Each of these cosmic speedsters, from the smallest particle to the largest structure, is a direct expression of the universe's fundamental laws in action. By chasing these extreme velocities, we are not just cataloging records. We are deciphering the rules of gravity, probing the nature of space-time, and reading the history of our cosmos, from its explosive beginning in the Big Bang to its accelerating future driven by dark energy. This grand cosmic race places us in a profound context. We live on a tiny world orbiting an average star, which itself is racing around a galaxy that is flowing toward a mysterious, unseen attractor. We are surrounded by high-speed phenomena, yet we are protected enough to observe, to question, and to wonder. Our search for speed is ultimately a search for understanding, a way to map our true location in the vast and dynamic tapestry of existence. So tell us, which of these 30 facts reshaped your understanding of the cosmos the most? Was it the oh my god particle, a single proton carrying the energy of a brick, or the haunting idea of the cosmological horizon, forever locking away parts of the universe from our view? Share your most mind-bending moment in the comments below. If you enjoyed this journey to the edge of physics and reality, make sure to subscribe. Our next adventure into the mysteries of space is already waiting. This astonishing illusion of faster-than-light motion is a direct consequence of the universe's ultimate speed limit playing tricks on our perspective. Picture a single car at night, racing down a long, straight highway directly toward you with its headlights on. The car itself is moving almost as fast as the light its own headlights are emitting. As the car gets closer, the light from its new, closer position has a shorter distance to travel to your eyes than the light it emitted a moment ago. If you were to measure its speed based only on the arrival times of these light flashes, you would calculate that the car is covering the ground between those 2 points much faster than it truly is, perhaps even faster than the speed of light itself. This is the core of the superluminal motion we see in jets from quasars and active galaxies. The material in the jet is not breaking any physical laws. It is simply moving toward us at such a tremendous fraction of light speed, perhaps 99.9%, that its own light is almost keeping pace with it. Our viewpoint compresses the time it takes for successive flashes of light to arrive, creating a powerful and convincing mirage of impossible velocity. This projection effect is not a flaw in our observations, but rather a powerful confirmation of the relativistic speeds at work. By carefully measuring the apparent speed of these moving knots and factoring in the angle of the jet, astronomers can actually calculate the true, breathtaking velocity of the plasma, confirming that we are indeed witnessing one of the fastest directed flows of matter in the entire cosmos.